So we left off with copper. Copper is one of the exceptions we just have to memorize because it doesn't tell you on the periodic table. But copper is going to be 4s1, and one of the s electrons got promoted to fill the 3D subshell. And there's going to be additional stability from the 3D subshell. After copper comes zinc. With zinc, we'll just fill in that missing 4s there. And now we've filled the 4s and the 3D. And then we go from zinc, we go to gallium. Gallium is going to have an electron in the 4p. So this would be gallium. And then we go to germanium. And then we go to arsenic here. And so let's stop at arsenic. And then let's take a look at the electron configuration for arsenic. For arsenic, As, it's going to be argon, and so everything's filled through argon, and then we'll have 4s2, 3d10, 4p3. This is the order that they fill. Then we'll rearrange the order to see the order in which they're going to react. In what order will they react? Well, we'll just put this in numerical. 3d10, 4s2, 4p3. Now, when they react, let's say an oxidizer comes along. The oxidizer is going to attack the outermost electrons, right? If an oxidizer comes along and attacks the outermost electrons, which electrons will it hit first? It'll hit the 4p electrons first, right? And then the 4s. And likely it's not going to touch the 3D because that's what we call filled. And so when we look at arsenic, how many valence electrons does arsenic have? It has 5 valence electrons. And the rest we call core electrons or inner shell electrons. Maybe we shouldn't call it core because, normally when we think about a core, it's filled, totally filled shell. Well, this is only a filled subshell, so it's like a pseudocore configuration. Or we'll just call it an inner shell electron. And so the outer shell electrons will be attacked.
In this case, one subshell is not more penetrating than the other?
You mean these?
Yeah.
In this case, the S are more penetrating than the P. And so if you're going to lose them, you'll probably lose because both of these are going to have the same quote unquote effective distance, right? This is n equals 4.
Can you go over pseudo double configuration? Or are you going to do it?
Pseudo, well, this would be the Nobel gas electron configuration.
Yeah.
But on top of that, we have the 3d10.
Pseudo?
And so this is what I mean by pseudo. It's not perfectly Nobel gas, but we got an extra. But the 3d10 is filled. Since it's filled, it's kind of unreactive in that sense. And so for arsenic, we say arsenic has 5 valence electrons. Do you know what the common oxidation states for arsenic are? The common oxidation states for arsenic are +3 and +5. +3, how does it get a +3 oxidation state? Well, some oxidizer comes along and plucks off all 3 p electrons. Boom, boom, boom. That's +3. Well, if you got a strong enough oxidizer, you can oxidize it to +5. +5 will come when it plucks off the remaining s electrons here. Right? Yeah. And so +3 and +5. Another thing about arsenic is arsenic has the same number of valence electrons as phosphorus, nitrogen, etc. Except when you look at, you look at phosphorus. Do I have phosphorus here? No, I don't have that family. When you look at a family, like let's look at the halogens. The halogens are going to be fluorine, chlorine, bromine, iodine, actinium. They all have the same number of valence electrons. And so when we look at it, well, how many valence electrons does fluorine have? Well, it has the 2s2 and the 2p5, a total of 7 valence electrons here. But if we go to chlorine, the same thing, 7 valence electrons, the highest end shell. When we go to bromine, we look at bromine, there's this 3d10 stuck out here. And so it's going to be argon 3d10, 4s2, 4p5. Do you see they wrote it in order of being attacked? Well, how many valence electrons are here? They also wrote it in order of valence electrons because we would consider the 3d part of the inner shell, and the outermost shell will be the 4. And so this is actually 7 valence electrons, even though it has this 3d stuck in there. And the same thing with krypton. It has a 4d stuck in there, but it still has 7 valence electrons. And now actinium. Actinium has a 4f, but the 4f is filled. That's a filled subshell. The 5d is filled subshell, so these are inner. And then the outer here are going to be the valence. And so we don't define necessarily, because if we define it as the outermost shell, the outer shell electrons, then this is wrong because the 3d is part of this shell here, right? And so we have to define it based on n level, because even though the 3d are part of the shell, it's part of the shell because of energy, not because of distance, right? And these 3ds are actually much closer to the nucleus than the 4. It just so happens that these aren't very penetrating, and therefore their energy is higher. Okay, but it's not in the sense. And so when we look at a shell is, a set of closely spaced orbitals in terms of energies. Well, that's arsenic. Let's look at some others here on the periodic table. For example, let's look at tin here. Tin would be krypton, right? And then we go here. This would be 1, 2, 3, 4, 5th shell. So this is 5s2. And then this would be 4d, 10. And then 5p, 2. So how many valence electrons does tin have? The highest n level. So 5s2, that's 2, 5p2, that's 2, that's 4. So tin has 4 valence. And so the easiest way to write this is krypton. We don't write it. We're going to write it 3d10, just in numerical order, 5s2, 5p2. But it would look like this because, when we fill these, the 5s would be here. So we fill the 5s first, and then we fill the 4ds, and then the 5p's come above that, like this, and so we got 5p with 2. And so it's kind of weird, but our valence electrons are these, and this would be part of the inner shell electron, which goes with the krypton core down here, right? Do you know what the common charges of tin are? Look, what's the common charge of tin? 2 and 4. Now, how does tin get a +2 charge? Tin 2 is very common. Tin 2 is very common because an oxidizer comes along and plucks off these 5p electrons. If you have a stronger oxidizer, they can also pluck off the 5s electrons, which are more penetrating. And so the common charges, tin 2 would be, we lost these 5p electrons. Tin 4, we lost these 5s. What about tin 5? Is tin 5 a very common charge? No, because tin 5, we'd have to break the spherical symmetry of the d subshell. The s is not so significant. We break it, yeah, but so chapter 9 is just a continuation of this. So let's take a look Here, chapter 9 is just applying some of these concepts to some properties of the elements. First one is just a broad classification. Well, actually a little bit of history first. You know, Mendeleev came up with this periodic table, and others, you know, came up with the periodic table just based on chemical properties. And then they were able to arrange things in that kind of order due to the properties. So this is Mendeleev's periodic table. There are some blank spots here, 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 because those elements hadn't been discovered yet. But later on they were, and then he filled it in. Well, what is the basis of the periodic table? The basis of the periodic table is actually, let me just skip this here. Or the way it's organized is it's just based on chemical families that have the same valence shell electron configuration. The chemistry is going to happen at the valence shell. You know, the core, the inner shell electrons aren't very reactive. And when we look at the chemistry, you know, we divide the periodic table into the metals. The metals are on the left. What is the definition of a metal? Well, metals have certain properties that are observed, which are malleability, ductility, electrical conductivity. Those are physical properties. And then chemical properties. The chemical properties are important because metals tend to lose electrons when undergoing chemical reactions. And so the species on the left side of the periodic table lose electrons. The species on the right side of the periodic table tend to gain electrons. And we've been using this all along because we've been looking at the periodic table to figure out the charges on the species. And so, let's see the ions here. Well, let's use this. And so we have the noble gases. And so, for example, lithium is a metal. They tend to lose electrons. So how many electrons will lithium lose? Well, lithium is going to lose 1. Lithium has 3 electrons. If it loses 1, it'll be like helium, and we'll have the core, helium core. Sodium is going to lose 1. And so all these have 1 valence electrons, and they'll lose 1. All these have 2 valence electrons, they'll lose 2. Then we're at the core. Aluminum has 3 valence electrons, it loses 3. And so we use the nearest Nobel gas to figure out what the charge is going to be. The metals are going to lose electrons to be isoelectronic, that is, to have the same number of electrons as the nearest Nobel gas, because once we hit the core, then those are going to be very difficult to ionize. Then we have some that are called the pseudo-noble gases. And the pseudo-noble gases are like this. The copper family is called the pseudo-group 1 elements, copper, silver, gold. The reason why the copper family is called pseudo-group 1, copper, silver, and gold. Copper, silver, and gold are pseudo-group 1 because they all have 1 valence electron, essentially. Is if we look at the electron configuration for copper, electron configuration for copper is argon, 3d10, 4s1. That's 1 valence electron. And so copper, a charge on copper should be +1. But do you know what the most common charge on copper is? The most common charge on copper is +2. And so that's kind of weird because if we're at +1, we've lost this 4s electron. And at +2, we have to break the spherical symmetry of the D. And if we're at copper +2, this is going to be 3d9. It's like a slice of pie is missing out of the pie. It's not going to be balanced anymore. Why is that? Well, there's an alternate reason why it's D9. D9 stabilized by another effect, which you'll learn about in Chem 1B, called the crystal field stabilization energy. Otherwise, D9 wouldn't happen, and we just have copper. Silver doesn't do this. silver behaves like you'd expect because there's only one charge on silver. What is the charge on silver? +1. It's a single charge species, and that's going to be because it's krypton 4d10 5s1. And so it just has one valence electron. Silver is only going to lose that, and then once it's lost that, it's pretty unreactive. And silver +2 doesn't happen. And so that means these 4d10s are quite stable. And so this is what they call pseudo Nobel gas, because the filled D subshell is fairly stable, like a Nobel gas, but it's not as stable because, you know, copper's D subshell gets attacked. Gold, the common charges for gold are +1 for sure, and also +3. And so gold is a little bit more tricky, but you know that +3 charge is stabilized in a different fashion. But +1 are common charges, so this is why we call this pseudo group 1, because it's like the alkali metals. All the alkali metals have one valence electron, all these have one valence electron as well. But these are a little bit more complicated. There's also pseudo group 2. Pseudo group 2 is zinc and cadmium. Zinc and cadmium are always +2. Zinc is always +2 because when we look at zinc, zinc is argon, 3d10, 4s2. And so it has 2 valence electrons. It loses those. We get Zn2+. Zn2+ is stable, only one charge. And the same thing with cadmium. You know, cadmium is krypton, 4d10, 5s2. And we lose those. We're stuck with this, which is stable. And so zinc and cadmium are just single charge, and so these behave nicely as pseudo group 2 metals. And then we have something called the 18+2. What is 18+2? Well, 18, where does that come from? That comes from argon, here. And so we have the 18+2 block. The 18+2 block are the 4 P's, here. Because if we fill these up, 2, 4, 6, 8, 10, we get to 18 electrons here, actually, and then the +2. We got to eliminate that, 18+2. All right, and so what are the 18+2? 18+2 is like tin. Why +2? Well, why +2 is, if you look at tin 2, let's look at the electron configuration. Tin has an electron configuration of argon, 3d10, 4s2, 4p2. Oh, tin? Oh, yeah, sorry. Tin, yeah, krypton. Actually, I got to change this. I want that. Tin is krypton. Actually, let's use the periodic table here. 5s2, 4d10, 5p2. 5s2, 4d10, 5p2. I'm not going to rearrange it. This is how we fill it. Either way is fine. You can rearrange it if you want. Now an oxidizer comes in. This is tin. An oxidizer comes in and plucks off electrons. Which electrons is it going to take first? It's going to take the 5p2, right? And so tin 2 with a 2+ charge has an electron configuration krypton, 5s2, 4d10. Now, where does the 18 come from? You know where the 18 comes from? It takes 18 electrons to fill the S, the D, and the P. That's 18 electrons. And so the 18+2 rule, actually, you know, forget this 18+2. The 18+2 is like this. It's going to be krypton, 4d10, 5s2. This is your 18 here, quote unquote. This is your +2 here. Right? We've already done the 18 plus 2 rule, and that is the common charges are like this. For arsenic, the 18 plus 2 rule says that the common charge would be, if we kept these s electrons, these d's are part of here, this would be 18 plus 2 to here. 18 plus 2. That means the 18 plus 2 rule says that plus 3 is a common oxidation state for arsenic. And so let's try not to complicate it too much, and then let's just look at some common oxidation states for some of these. Lead. What do you think the common positive charges for lead are? Well, when we look at lead, this would be what? 1, 2, 3, 4, 5, 6. So lead is going to be 6s2, then the 4f, and then the 5d, or the 5d and the 4f. You know, it gets all mixed up. And then we go to 6p2. So 6s2, 6p2, that's its valence electron shell configuration. And so if lead is, if lead metal is this, you know, it's got the whatever core plus other stuff, you know, which is the 4f14, 5d10, and then 6s2, 6p2, then the plus 2 is this. This is your plus 2, this is your 18. 18 plus 2 gives us a charge of, that is, eliminate these, and lead should be a plus 2 ion. And so lead plus 2, is it common? Yeah. But if you have a more powerful oxidizer, you can get rid of the plus 2 and go to 18, which is plus 4. And so lead comes in lead 2 and lead 4. Those are the common charges. But, you know, lead 4 as a free ion is tough. Are you familiar with very many 4+ ions? No. When you get to higher oxidation states like plus 4, plus 5, plus 6, it's stabilized in polyatomic ions. You know, you have some oxides in there. And so usually when we get to these higher charges, we write it in Roman numeral to indicate that it's not a free ion. It's been stabilized by something else. And so we can use that rule to predict things like, what do you think the charges on indium are? Indium is 5s2, 5p1. Use the plus 2 rule. And so indium, you'd expect charges of plus 1 and plus 3. Thallium, you'd expect plus 1 and plus 3. Antimony, plus, well, we got 3p electrons, so plus 1, plus 2, plus 3. We lose those. Plus 3 and plus 5. That's the 18 plus 2 rule. 18 plus 2 rule means knock off the p's, leave the s's. The s's are the plus 2. And so you knock off the p's, what's the charge? That's a common oxidation state. And then get rid of the s's, get rid of the plus 2, and that's the second common oxidation state for those. The others are mixed up here. I'm not sure why it's organized like this. Chromium 2+, manganese 2+, iron 2+, nickel 2+, cobalt 2+, copper 2+ doesn't belong. But all these are the same. All these, you're losing the 4s2. If we lose the 4s2, then we're going to form plus 2. Okay? And so, for example, iron, a common oxidation state for iron is, well, iron is argon, 4s2, 3d, and count it out. 1, 2, 3, 4, 5, 6. 3d6. If we go to iron 2+, it's going to be argon, 3d6. And so common oxidation state of iron is iron 2. Now, if we have a powerful enough oxidizer, the powerful enough oxidizer can attack this. If it attacks that, then we can go to iron 3 plus. Iron 3 plus will be argon 3d5. 3d5 is a half-filled subshell. How about iron 4? Do you think iron 4 is a common oxidation state? No. And so we have iron 3 here, chromium 3 here. You know, if we got enough strength in the oxidizer, we can pluck off a D as well. Uh-huh.
What is 18? Why 18?
Why 18?
Yeah, what does that mean?
Okay, to fill this shell, the first shell takes 2 electrons. To fill the second shell takes 2, 4, 6, 8 electrons. 8 electrons we call an octet. To fill the third shell takes 8 electrons, an octet. To fill the fourth shell takes how many electrons? Count them. To fill the fourth shell takes 18 electrons. And so 18 electrons would be isoelectronic with krypton. And so 18 electrons comes from filling this type of shell where you have SPD. And so 18 electron, because most of the time what we're looking at is the fourth period, you know, the fourth shell. And so that's the origin of the 18, but we can apply the 18 electron rule to everything, you know, because it all behaves the same. And so I don't take it literally. If you take it literally, it doesn't add up, right? Because if you throw on the F block in there, then it's no longer the 18, but then they'd have to come up with the next one, which would be 14 plus 18, which would be the 32 electron rule. And do you want the 2 electron rule, the 8 electron rule, the 18 electron rule, the 32 electron rule? It gets too much. And so that's just to know, you know, it's general. And you don't have to worry about, okay, define the 18 electron rule. No. You know, you just have to know how to use it. You know, what's the common charge of thallium? If you know +1 and +3, then you already know it. You know the 18 electron rule. Even though technically that should be the 32 electron rule. Something like that, you know. We aren't going to worry about it. And so we can use periodic properties to figure out common charges for ions. Okay, that's for losing. Metals lose, non-metals gain. And so it's pretty simple here. Carbon wants to gain 4, nitrogen wants to gain 3, oxygen wants to gain 2, fluorine wants to gain 1. And that holds for the whole families here. The carbon family, the nitrogens, which are called pnictogens, oxygens, which are the chalcogens, fluorine, which is the halogen family. You don't have to know the names of the family. But basically what we do is we just complete the octet here. So that would be the 8 electron rule. Down here, we you know, as we go further down, it would be the 18 electron rule, and then pretty soon the 36 electron rule, or 35 electron rule. No, 36. Hydrogen can gain or lose. Okay, another thing we can understand based on the periodic table is the atomic radius. Unfortunately, the atomic radius is hard to define. It's hard to define because an atom consists mostly of an empty space. And then, you know, you have an electron cloud here. But there's no wall or barrier. So if you're trying to measure, you know, the radius of this, it's very difficult because, you know, if you have a small probe, let's say a probe smaller than an atom, which you aren't, but imagine a probe smaller than an atom, where does it stop? You know, when you hit the nucleus? And so what we look at you know, electrical potentials. That is, you know, the closer this gets, the more negative charge density it runs into, and the more repulsions there might be with your probe. And so we're looking for voltages and trying to keep the voltages the same. So at what voltage do you call that the wall? Well, that varies. And so what we do to measure radii is we try to bond it with something else. Because, measuring where the electron is tough. Measuring where the nuclei are is not tough. And so even though there's mostly empty space, electrons in there, the nuclei don't suffer nearly as much as electrons do from the Heisenberg uncertainty principle. Heisenberg uncertainty principle says, we aren't going to pinpoint the electrons and know the energies simultaneously. But for the nuclei, we can pinpoint the nuclei in space. There's no problem. And we can do that very accurately. And so if we can bond two sodiums together and then measure the distance between the nuclei, that's called the bond distance. And then if we cut the bond distance in half, then we have the radius of the sodium atom. But the problem with that is it depends. For example, if you only have two sodium atoms, then they bond at 157 picometers. But if you have multiple sodium atoms in a sodium crystal or a piece of sodium metal, then they bond a little farther apart. There's another sodium here, another sodium here, another sodium here. So this isn't showing it completely. Whereas this is what we call a molecule of sodium, which is going to be unstable, just two sodium atoms bonded together. And so what happens is the radius changes depending on how strong the bond is. If there's a very strong bond, then the atoms get closer and closer together. If it's a weak bond, the atoms get further and further apart. Now, if you're measuring the radius based on the bond distance, then the radius is going to change. And so what we see is that the radius varies from compound to compound. If the radius varies, then the best thing to do is just take the average radius of a sodium atom. Ions are going to have a different radii because of the charge. And so when we take the averages, we come up with a table that looks like this. So in oxygen-containing compounds, it depends on how strong the oxygen, how strongly it's bonded to whatever other atom you have in there. And so what we see here is the average radius of an oxygen is 73 picometers. What we don't see is the spread, because whenever we report an average, we'd like to know how wide the spread is. Does the oxygen radius vary widely, or does it not vary much at all? And so what would give us an indication of the spread? We need a 73 plus or minus some kind of spread to give us an idea, what kind of variation we observe in oxygen radii. And so what would you do here, or how would you report this to indicate the precision or, the variation of oxygen radii? What gives you an indication of the variation of radii, or variation experimental results like percent sulfate from trial 1 to trial 3? Or the concentration of red food color? What gives you the indication for the variation in that? How do we report averages? We would report the average plus or minus the confidence level. And so we're missing the confidence level. The confidence level will give us an indication, because if the sample size is small, let's say very few compounds were measured, then smaller samples will have a wider range. The more samples you run, the narrower range you get. Probably the best trade-off is taking how many samples? About 3, right? 3 is a dramatic improvement over 2. And then the standard deviation tells us the spread. So we don't know how wide the spread is. We just have the average here. And so when you look at this number, you don't treat it so accurately because, there's some uncertainty there. Is the oxygen really going to be 73? Well, it's going to be close to it, probably. We don't know how big the spread is. And so we have the values here. Now, one of the things you'll see is this. You're looking at the gold. When we look at the gold, lithium starts off big, 152, and then it shrinks down to 71. And the same thing, this pattern's repeated. Sodium's big, chlorine's small, potassium's big, bromine's small. And so as we go left to right in the periodic table, the size decreases. And so one of the things we want to understand is why do we see this? Going across a period, we see decreasing radius. And so the answer is this. As we go across, it should grow bigger, shouldn't it? Because as we go across here, in sodium we have 11 protons and 11 electrons. In magnesium we have 12 protons and 12 electrons. Well, 12 protons and 12 electrons is more stuff. If you have more stuff, it should be bigger, right? But it's getting smaller, which is odd. And so what is the reason it's getting smaller? The reason it's getting smaller is because of this. When we look at sodium, sodium has 11 protons in the nucleus, and then it has 10 electrons as its inner shell or core. Those 10 electrons would be like neon. And so it's a neon core, and then it has one valence electron out here. Well, magnesium has 12 protons. And so when we have 12 protons versus 11 protons, 12 protons is going to have a stronger pull on the electrons. And so magnesium is going to have the neon core of 10 electrons, but it's going to be pulled in more tightly because there's a stronger positive-negative attraction. And so the core orbitals in magnesium are smaller because of the higher Z. But now you have 2 electrons out here. What's most important in dictating size is the outermost electron. How much positive charge does the outermost electron see? The problem is shielding. The outermost electron is going to be shielded from the nuclear charge by the core electrons. And the core electrons are very effective shielders of nuclear charge. In fact, for every proton, 1 core electron is enough to cancel out that charge. And so if I have 10 positive charges here and 10 negative charges, the net charge, or Z effective here, is going to be about 1, plus 1. And so this electron out here is going to see about a plus 1 charge. Now, the same thing happens here. Except when I look at this electron is a same shell electron. Same shell electrons are not effective at shielding because this electron might be over here. Sometimes this electron's here, so it can shield a little bit, but not as much as a core, usually. So same shell electron is not as effective at shielding. This is compared to core electron. And so when this electron sees the nuclear charge, the Z effective is not going to be close to 1. The Z effective is going to be closer to plus 2. Because here we have 12 positive charges being canceled out by 10 negative charges. And so Z effective is closer to plus 2. This is a very crude calculation. In your homework, you'll do a more accurate calculation of Z effective using Slater's rules. But for us, that's pretty much it. And so this explains why magnesium is smaller. Magnesium is smaller because the electrons are going to be pulled in closer to the nucleus. The orbitals are going to be smaller. Yeah. And so the radius decreases because Z effective increases. And Z effective increases because as you're going across, you're adding a proton, which increases Z. At the same time, you're adding a same shell electron. A same shell electron doesn't really shield much. And so you can see here the radius is going to decrease because we're increasing Z and at the same time adding a same shell electron. The radius decreases here because we're adding protons. And those protons aren't being effectively shielded because we're adding a same shell electron. Let me erase this here. But when you look at the size here, it gets smaller, right? Bigger, smaller. Add a proton, add a same shell electron. Same shell electron doesn't shield much. Extra proton means Z goes up. Z goes up. But here, take a look at what happens here. 125, 124, 124, 125, 125 picometers. Here the size is flat. There's no change. Why isn't it shrinking? Because each time, like for example, when I go from chromium to manganese, I add a proton and I add an electron. The proton should be increasing Z. The reason it's flat here is because of this. For the transition metals, I add a proton that's going to increase Z, but I'm adding a 3D electron. Is a 3D electron an inner electron or an outer electron compared to 4s? It's an inner. And so when I add the proton, I also add a inner shell. Here's where the nomenclature gets, because this is all part of the fourth shell. But we're saying that that 3D is much closer in proximity to the nucleus. And so we add an inner shell, i.e. 3D electron. And what we're looking at is the outermost electrons. The outermost electrons will dictate the size. The outermost electrons will be the 4s. Right? And so what happens is these inner shell electrons are effective shielders. And so if I make a plot of the sizes, I'll see this here. If I make a plot of the sizes, we start off with lithium and go to fluorine. So I go across a period, the size shrinks. Lithium's the biggest one, fluorine's the smallest one. And I add a proton, I add a same shell electron. Same thing, the next period. This is second period, this is third period. Shrinks. Fourth period, I have the Ds. Here's the transition metals. The transition metals stay flat because I add a proton, but I also add an inner electron, which shields it. So it cancels each other out. So the Ds will do that. And lanthanides do that as well in the F block because we're adding an inner shell electron there. And so the transition metals and the lanthanides, which are the Fs, the first Fs, will do it. And the second Fs will do it as well. Okay, the next thing is this. You know, the size also increases depending on what shell you're at. So when we go from sodium to potassium here, what's happening there? With sodium, we have 11 protons, 10 inner shell, and 1 outer. And so Z effective here is going to be about +1, just crudely. For potassium, we're going to have 19 protons, but we'll have 18 core electrons. In fact, we're going to have a whole nother shell of electrons in here, and then we'll have our valence. And so Z effective here is close to 1, because these 18 inner shell electrons will cancel out 18 of the positive charges, leaving a +1 for that electron to see. And so the reason this increases is because even though this has a lot more protons, 19 protons versus 11 protons, Z effective is about constant. Z effective doesn't change much. And so as we go down, we're adding a shell of electrons. And therefore the size increases as we go down the radius. The next thing we have to look at are the ions. So let's take a look at the ions next. If we look at sodium, sodium had 11 protons, 11 electrons. Sodium plus, though, sodium plus will have 11 protons and then just 10 electrons. And its valence electron will be gone. So now we have 11 protons attracting 10 electrons. It's going to pull in the electrons closer, versus 11 protons attracting 11 electrons. And so what happened to the size? The size went from 186 to 99. And so it got cut in half, roughly. Magnesium lost 2 electrons in going from magnesium to magnesium 2+. This is approximately half the size, even though it lost 2 electrons. And so we take a look at the pattern here. Potassium versus potassium ion, 227 to 138, about 1/2. 197 to 100, about 1/2. 161 to 75, about 1/2. All these are about 1/2, even when we look at multiple charges. So iron goes to iron 2, the size gets cut in about 1/2. Iron 2 goes to iron 3, it didn't get cut in half again, right? It stays about the same. And so iron to iron 3 is about a little more than 1/2, right? And so what we can say is, crudely, because this isn't very accurate, nor very precise, what we can say are cations are about half the size of their parent atom. Anions, if you take a look at what happens with the anions, fluorine to fluoride, it doubled. Oxygen to oxide, even though this one gained 2 electrons rather than 1 electron, the size about doubled. And so what we can say about the anions are about twice as big as their parent. This is about 2 times. So an interesting thing happens here. The interesting thing is that now we're going to look at the blue and the green. For the neutral atoms, the biggest are on the left. For the ions, the biggest are on the right. For the neutral atoms, the biggest neutral atom is at the bottom left, because it has the most shells and the lowest Z effective. The smallest neutral atom is at the top right, because it has the fewest shells and the highest Z effective. And for the ions are going to be, the smallest ions are going to be on the left, the biggest ions on the right. The smallest ion will be at the top left, the biggest ion will be at the bottom right. And so it's flipped. It's not going to be totally at the bottom right because it would be in one. So if we look at iodide and telluride, telluride's a little bit bigger. There's 2 electrons rather than 1. And about double. And so the general trend here is that when we look at all the cations, the biggest cation is about comparable to the smallest anion. And so, with a few exceptions, what we can say is that cations are smaller than anions. Now, that's not a law, since there are a number of exceptions, but just a general rule. Cations are smaller than anions. And so how big are atoms in general? You know, what's the biggest atom that you see here? The biggest atom is rubidium. What would be bigger? Cesium. Cesium's close to about 300 picometers. And so 300 picometers means a diameter of about 600 picometers. And so the biggest atom is going to be about 600 picometers. Cesium ion would be about 300 picometers, right? And then it shrinks down over here from 248 down to 133, so it gets cut in about half. From 227 to about 114, so it gets cut in half as we go across. The smallest atom would be hydrogen or helium. What would be smaller, hydrogen or helium? Maybe drawing it out might help. Hydrogen has 1 proton, 1 electron. Helium has 2 protons and 2 electrons. Do one of these electrons shield the proton completely? No, because they're same shell. If there are 2 protons here, then this electron is going to be pulled in, and this electron is going to be pulled in. And so it turns out that hydrogen is going to be a lot bigger than helium, because helium is going to pull in. And so we have a higher Z effective. We add a proton and we add a same shell electron, which means it's smaller. Z effective goes up. And so helium. But this is going to be about 100 picometers. So atoms range in size from about 100 picometers or 1 angstrom to 5 or 6 angstroms. And we talked about that in chapter 2 a long time ago. We'll talk about it here. At this size, I don't have too much more to talk about, but let's take a break and then we'll finish this up.